viewers, welcome to Ozone Day celebrations once again. Ozone is the only major atmospheric constituent that absorbs significantly between 210 and 290 nanometers. Without ozone, life would have remained underwater. So, ozone is the only major atmospheric constituent which absorbs UV light. And without ozone, life would have remained underwater. Life would not have been possible as it is. So we say it is because of ozone that we are surviving on Earth. All UVC is blocked by diatomic oxygen or by ozone in the stratosphere. The ozone layer also blocks most UVB. Only 5% of this reaches the Earth, and you are aware about it. UVA is hardly absorbed by ozone, and most of it reaches the Earth. Thus, UVA makes up almost all the UV light that penetrates the Earth's atmosphere. Now, the normal ozone concentration is about 300 to 350 Dobson unit. Decrease in concentration of ozone and thinning of ozone layer is called ozone depletion. The ozone layer has historically protected the Earth from harmful UV rays. In recent decades, the protection has diminished due to stratospheric ozone depletion. Modern industries and our day-to-day life uses refrigerants and or aerosols, foams and soaps, which result in the emission of many gases like fluorochlorocarbons, that is CFCs, hydrochlorofluorocarbons, that is HCFCs, and halones, which are haloalkanes, methyl bromide, carbon tetrachloride, methyl chloroform. Halogens get evolved in atmosphere, which are mainly responsible for ozone depletion, as they contain or produce chlorine free radical. So what we find that because of the pollution in the troposphere, the gases like nitrogen oxide by burning of fuels, CFCs, chlorine, bromine, these are now liberated, and they very slowly go on to the stratosphere. Their half-life in the stratosphere, or they stay in the stratosphere for very long time, and they result in the ozone depletion. So we say that rampant combustion of fossil fuel, extensive use of nitrogen-based fertilizers, sewage treatment plants and other industrial processes that involve nitrogen have resulted in the emission of levels of nitrous oxide. This anthropogenic activity, that is human activity, is also responsible for ozone depletion. In the wake of success of the Montreal Protocol, the CFC usage has been controlled. But nitrous oxide possesses a greater threat to the ozone layer today. Remember this. In 1969, Dutch chemist Paul Crutzen published a paper that described the major nitrogen oxide catalytic cycle affecting ozone levels. Crutzen received the Nobel Prize in Chemistry in 1995 for demonstrating that chemical compounds of nitrogen oxide increase the destruction of stratospheric ozone. Crutzen shared the Nobel Prize with American chemists Mario Molina and F. Sherwood Rowland, who discovered in 1974 that manufactured chlorofluorocarbon gases also contributed to ozone depletion. Crutzen demonstrated that nitrogen oxides can react with free oxygen atoms, thus slowing the creation of ozone. And they can also decompose ozone into nitrogen dioxide and oxygen gas. Nitrous oxide is produced naturally when nitrogen is consumed in soil or water by bacteria. Now this nitrous oxide rises into the stratosphere, where most of it is broken down into harmful molecules of nitrogen and oxygen by sun's rays. But some of this nitrous oxide can survive for hundreds of years. And when it is there in the stratosphere, it gets photolyzed into two reactive compounds, nitric oxide and nitrogen dioxide. Now these compounds react catalytically with ozone, breaking it down to oxygen. So as you can see on your screen, nitric oxide acts as a catalyst to break ozone gas into oxygen. So what does nitric oxide do? It reacts with ozone in presence of UV light, and in the process nitrogen dioxide and oxygen is formed. Now this nitrogen dioxide reacts with an oxygen free radical which is already in the atmosphere, in the stratosphere, and it gives us nitrogen oxide and oxygen. And this nitrogen oxide which is being formed here again enters the cycle, and the cycle is repeated. So when we look into the net reaction, what we find that ozone on reaction with oxygen free radical in presence of sunlight is converted into oxygen. Not only this, please remember nitrous oxide free radical is also a radical which destroys ozone. It is produced by lightning and by burning of oil and petrol by aircrafts. Scientists believe that humans' role in producing the harmful gas has largely been overlooked. 1/3 of the nitrous oxide emitted per year is anthropogenic, that is, it is of human activity. Fossil fuel combustion as well as nitrogen-based fertilizers, sewage treatment plants and other industrial processes that involve nitrogen all contribute to the higher nitrous oxide levels. Crutzen studies helped in shelving of the introduction of supersonic passenger planes, which would fly at a very high altitudes near the stratospheric ozone layer and produce nitrogen oxide from the reaction between nitrogen and oxygen into the air drawn from their engines. So this would have been very, very catastrophic. It would have been very dangerous. Now, although these supersonic transports never took off, current nitrous oxide emissions destroy as much ozone as flying 500 such planes a day. So imagine if the governments had allowed supersonic transport, the ozone layer would have been completely devastated or completely depleted. Global human emissions of nitrous oxide are roughly 10 million tons per year, compared to slightly more than 1 million tons from all CFCs at the peak of their emissions. So that means now the danger to ozone layer is from the emissions of nitrous oxide. That is, the danger is more as compared to CFCs, because the amount of nitrous oxide that is being emitted is 10 million tons per year, compared to slightly more than 1 million tons from all CFCs. Crutzen's work was a source of inspiration and paved the way for further work by two American chemists, Mario Molina and Sherwood Rowland. In 1974, they demonstrated how the man-made CFCs were splitting ozone molecules into atmospheric oxygen and chlorine monoxide molecules. Crutzen, Molina, and Rowland shared the 1995 Nobel Prize in Chemistry. Now, how does CFCs destroy the ozone layer? The strong winds carry CFCs up into the atmosphere, where UV radiation breaks them apart, releasing reactive halogen species. Stratospheric ozone is destroyed by reactions involving reactive halogen gases, which are produced in the chemical conversion of halogen source gases. The most reactive of these gases are chlorine monoxide, bromine monoxide, chlorine and bromine atoms. These gases participate in three principal reaction cycles that destroy ozone in the stratosphere. In cycle 1, we observe that solar radiation, that is the UV rays, breaks the CFCs and HCFCs to form chlorine atom, which then reacts with ozone molecule and forms chlorine monoxide. So what has been observed, that chlorine free radical reacts with ozone to form chlorine monoxide and oxygen. And now this chlorine monoxide then reacts with an oxygen free radical to form chlorine atom and oxygen molecule. As chlorine atom acts as a catalyst, one single atom can destroy large amount of ozone molecules. So when we look into the net reaction of the above two reactions, what we find that oxygen free radicals in presence of UV light, and it is dissociated to form oxygen. So the overall reaction here again is the same, which we saw was involved when the nitrous oxide was being produced. It was being converted into nitric oxide was converted into nitrous oxide, which then converted into nitrogen dioxide, which entered a chain. And the overall reaction there was also that ozone reacted with oxygen in presence of UV light to oxygen free radicals in presence of UV light to form oxygen molecules. And you have to remember that this cycle is most important in the stratosphere at tropical and middle latitudes, where solar ultraviolet radiation is most intense. Now, each chlorine atom can attack and break apart as many as 100,000 ozone molecules during the time it is in the stratosphere. The other two cycles which are involved in the dissociation of chlorofluorocarbons are cycle 2 and 3. And they operate in polar regions as the chloromonoxide and bromomonoxide are abundant there. The cycle 2, as you can see on your screens, is initiated by reaction of chloromonoxide with another molecule of chloromonoxide. This dissociates in presence of sunlight to give chlorine free radical. And this chlorine free radical reacts with oxygen to give us, reacts with ozone to give us oxygen. So net result here is also the same, that is the two ozone molecules are dissociated on reaction with free radicals to give us two molecules of oxygen. And in cycle 3, what we find that chlorine monoxide, as you can see on your screens, reacts with bromine monoxide to give us chlorine free radical, bromine free radical and oxygen. Now this chlorine free radical and bromine free radical react with ozone by two different pathways in presence of sunlight. In one pathway, a chlorine free radical reacts with ozone to give us chlorine monoxide and oxygen, whereas in the second pathway, bromine free radical reacts with ozone to give us oxygen. So again the net result here is that two molecules of ozone on reaction with free radicals, here they are halogen free radicals, is being dissociated to three oxygen free radicals. So what we find that the net reaction in both cases, that is cycle 2 and cycle 3, is that two ozone molecules form three ozone molecules. Visible sunlight is required to complete each cycle and to help form and maintain chloromonoxide in abundance. During polar night and other periods of darkness, ozone cannot be destroyed by these radicals. Ozone level of less than 220 is the result of ozone loss from chlorine and bromine compounds. Ozone holes are popular names for the areas of damage to ozone layer. The discovery of the Antarctic ozone hole was first announced in a paper by Joe Farman, Brian Gardiner, and J. Shanklin, which appeared in the Natural Journal Nature in May 1985. A major hole is now over Antarctica, where there are ice sheets. If these ice sheets melt, it could increase coastal flooding, causing a violent shift in climate. What we call the ozone hole is a thinning of protective ozone layer in the stratosphere above the Antarctica that begins every September. Chlorine and bromine derived from human-produced compounds are released from reactions on high-altitude polar clouds, which I have already discussed with you. The annually occurring ozone hole over the Antarctic is one of the largest and deepest in recent years. Analysis show that the hole has reached its maximum size. The 220 ozone hole grew rapidly from mid-August and peaked at around 24 million square kilometers in early October. It covers 23 million square kilometers above average for the last decade and is spreading over most of the Antarctic continent. This is what you can see on your screens also, that now the ozone hole is spreading and it has taken a very large size. With the universal support of 198 nations, the Montreal Protocol led to the phase out of almost 99% of ozone depleting substances. The Montreal Protocol is considered the most successful international environmental agreement to date. Countries all over the world have made a concerted effort to eliminate the CFCs, that is chlorofluorocarbons. While initial measurements in September caused concern, the overall trend is towards the ozone hole slowly closing as the result of the Montreal Protocol. And the estimates predict that it will return to pre-1980 levels by the 2060s. Now the question arises, is there a hole over Arctic? Unlike Antarctic, which is a continent surrounded by oceans, the Arctic is an ocean surrounded by mountainous continents. This means that stratospheric circulation is much more irregular here. Because the Arctic zone layer is not normally as cold as that of Antarctic, stratospheric clouds are less common. So, although a deep ozone hole over the North Pole is unlikely, ozone depletion can occur above the Arctic. When it does occur, it usually lasts for a short period of time. However, significant ozone depletion did occur in January 2020. If the size of the Arctic hole assumes the size of the ozone hole of Antarctic, it would expose nearly more than 700 million people, wildlife and vegetation to UV. So just imagine what will be the effect. So from this we can say, till now we can say that there is a ozone hole over Antarctica because of the conditions which prevail there. And whereas at Arctic, we expect the ozone hole is there, the occurrence is less because of the mountainous region which is surrounding it. So now the question is that ozone hole is being formed. Why? Because of the CFCs that we are using, halons that we are using, nitrous oxide that we are using, which go into the stratosphere and bring about free radical reactions and which result in the depletion of ozone. Now, knowing this, let us ask ourselves a question which is very relevant. Is the ozone hole linked to global warming? Yes. A side effect of global warming is that the temperature of ozone layer is falling slightly. This means that more of the stratospheric clouds can form over Antarctica and hence delay the recovery of Antarctic ozone hole. The Antarctic ozone hole can also help change the surface climate by changing where solar energy is absorbed in the atmosphere. Since the ozone depleting chemicals are greenhouse gases, so reducing their amount has significantly helped in combating climate change. Now, what are the harmful effects of ozone depletion or formation of ozone hole? So, till now we've discussed that ozone hole is being formed due to the anthropogenic activities of human beings. And because of that, the UV light, that is UV rays A, and to some extent UV rays B, are entering the earth. And now how does it affect us? It affects us greatly. First of all, the first thing that we have to keep in mind, that if we do not protect the ozone layer, it will have harmful effects on our health. The UV rays will cause skin cancers, which is also known as melanoma, sunburns, and premature aging of the skin. It will also cause cataracts. Immune system will be suppressed. DNA absorbs UVB radiation and changes its shapes by changing the pyrimidine dimers, which will result in faulty DNA, and this faulty DNA will give wrong information. The changes in the DNA results in mutated cells, or the cells die or show cancer. Damage to marine life, in particular plankton, which are tiny organisms in the surface layer of oceans, are threatened by increased UV radiation. Plankton are the first vital step in the aquatic food chains. So if they are destroyed, if they are damaged, the entire food chain will be disrupted and the aquatic life will be disrupted. Not only this, they also affect the animals. In domestic animals, UV overexposure may cause eye and skin cancers. Species of marine animals in their developmental stage, that is young fish, shrimp, larvae and crab larvae, have been threatened in recent years by the increased UV radiation under the Antarctic ozone hole. Not only this, materials like wood, plastic, rubber, fabrics and many construction materials are degraded by UV radiation. The economic impact of replacing and protecting materials could be very high. So it would affect the economy also. So what we find, that if ozone hole is depleted, UV rays will not discriminate between the living and the non-living. It will affect the humans. They will have cancers, skin diseases, animals who will again have the eye diseases, skin diseases, cancer, marine life, where the lower marine life would be affected, the larvae would be affected, which would disrupt the life cycle. And they would also disrupt the non-living by affecting the materials. So nevertheless, there is always a silver lining. And the silver lining to the ozone day is that the latest reports confirm that it has led to the phasing out of about 95% of the consumption of ozone depleting substances listed in the Montreal Protocol. So we know that because of ozone depletion there are negative points, but because of the Montreal Protocol there is a silver lining to the celebration of this ozone day, because the latest reports are confirming that there is recovery of ozone layer because we have stopped using to about 95% ozone depleting substances. In turn, this has led to the prospect of the ozone layer covering by 2050 to 2075. So what can we do now to preserve the ozone layer? We can carry out short campaigns, special events, competitions and essay writing activities at schools and colleges, a few of the everyday initiatives that can change people's attitude towards ozone protection. On our part, spreading awareness about the harmful effects of products having chlorofluorocarbons such as hairsprays, fresheners, cosmetics and aerosols in plastic containers should be our priority. Trees should be planted and backyard gardening should be encouraged. Environmentally friendly fertilizers must be used extensively. Get excess emissions vehicles checked and save on gasoline and crude oil usage by regular maintenance. Burning plastic and rubber tires will likely pollute the air. We can always opt for gadgets with Energy Star label and choose public transport to reduce carbon emissions. Please remember that we have only one Earth. Life on our Earth planet, as we know, would not be possible without the ozone layer. Earth without the ozone layer is like a house without a roof. So, on this ozone day, let us make a resolution that all of us together will save the ozone layer. Thank you.